You know about this. As far as SQ1 is concerned, I've always written SQ1 such that it has a bearing on important aspects of Bronsted-Lowry acid-base chemistry. And we've not yet gotten far enough into this subject so that you would be able to wrestle successfully with SQ1. So be patient. We can have these SQs anytime. I prefer to have them when they mesh with the material that I wish the SQ to cover. So I expect I'll probably issue the SQ this weekend or early next week, because I expect by that time we'll be far enough into the acid-base stuff for you to get at it successfully. That's what we want. Now, writing equations for acid-base reactions. We began to talk about this yesterday. It establishes the qualitative aspect of Bronsted-Lowry acid-base chemistry. And it's achieved by writing correct PSIs and then following the rules. We finished yesterday by looking at D, which was in regard to diluting aluminum nitrate solution. And by support of the acid-base table, we recognize that aluminum ion in water solution will convert to the hydrated aluminum ion, which is a Bronsted acid. You see by examination of the table, is just underneath position-wise acetic acid. And today when we talk about K values, which I expect you could infer from the K values printed, 1.8 times 10 to minus 5 for acetic acid, 1.4 times 10 to minus 5 for hydrated aluminum ion, tells you that these two acids are very near each other in strength. So water solutions of these acids, if they're at the same molarity, will show about the same pH. And you'll do work regarding this in assignment 4 in 46L for hydrated aluminum ion. Now, when you diluted that system, you added water to the equilibrium, hydrated aluminum ion plus water, double arrows, hydronium ion, and the conjugate base of hydrated aluminum ion. Well, in essence, you added a reactant. And when you add solvent, you always provoke the reaction to occur that involves solvent. Doesn't the reaction hydrated aluminum ion plus water demand recognition that for that reaction to proceed, hydrated aluminum ions have to meet with water molecules? Nothing more, that's what it says. So if I up the ratio of water molecules to hydrated aluminum ions, which is what I do when I add water, do I not then give a better chance for hydrated aluminum ions to meet with water molecules and react successfully? No more, no less. So for system E, just turn the tables around. Because in system E, we're talking about taking an acetic acid solution in which this chemistry exists. Because when acetic acid solution is prepared, the weak acid acetic acid reacts with water, make hydronium ion and acetate ion, the extent for which is generally small. If the initial molarity of acetic acid is large, guaranteed to be small. We'll talk about assessment of extents quantitatively in just a few moments when we get at this Ka, Kb stuff. Well then, in any water solution of a weak acid or weak base, where the ionization reaction with water of the solute has not gone to an extent of 100%, equilibrium involving the solute on reaction with water is established. So the question really is for E like it was for D. What impact do we exert on this equilibrium if we do something regarding the content of the system in solvent? For D, we added solvent. E, we're going to remove solvent by evaporation. Well, does this not diminish the opportunity for acetic acid molecules to react with water to convert to products? Because I've lowered the ratio of acetic acid to water. So if you look at it from that standpoint, we're like a teeter-totter I'm removing water from this system, so clearly the reaction which must occur to get me back to equilibrium is what? Right to left or left to right? Right to left, done. F, potassium hydroxide solution. K plus hydroxide ion and water. To be combined with sodium hydrogen carbonate solution. Sodium ion, hydrogen carbonate ion, and water. G. Once again, sodium hydrogen carbonate solution is to be considered for G. But this time for G, the sodium hydrogen carbonate solution is to be mixed with sodium hydrogen sulfate solution. Do you think we'll get different chemistries for these systems? Well, you know how to play the game. For system F, look at the acid-base table. In making the mixture called for system F, what's the strongest acid in our PSI? Use the table. That's why we've given you the table, so that you will be able to use it. The strongest acid in this PSI. Now, in making this search, I want you to look at the formula for the hydrogen carbonate ion in the acid-base table. You see anything interesting and unusual about this species? You see that its formula is in the acid column. Do you see that it's taken a position above water in the acid column? So hydrogen carbonate ion is a stronger acid than water. Now look at the base column. You see hydrogen carbonate ion in the base column? Do you see it takes a position lower than that of water in the base column? What's that mean? Hydrogen carbonate ion is a stronger base than water. What an interesting critter. It is both a stronger acid and a stronger base than water. There are a few other species which exhibit this property. You'll see some of the formulas for such species in their acid-base table. We're just telling you more about how to read this table and understand it. So for F, PSI strongest acid, hydrogen carbonate ion. Strongest base, hydroxide ion. So this is the reacting acid, this is the reacting base. Acids give away H+, bases grab H+. So I'm making as my product acid water. And my product base carbonate ion. Last part of the puzzle, extent. Large or small? Large. This acid is stronger than this acid. We just talked about that. And the table, of course, reminds you that hydroxide ion is a stronger base than carbonate ion. As it must be. Hydroxide ion isn't going to react with something to make it to form a stronger base than hydroxide ion, not in water solution. Remember the leveling effect? The fact that in water solution, the strongest base which can ever be present at high concentration is in fact hydroxide ion, the conjugate base of the solvent. Okay. That takes care of that. Now let's go to G. Once again, sodium hydrogen carbonate solution is part of system G. Oh, I erased it, but so I'll put it back. But for system G, what's the strongest acid in our PSI? What is it? This it? You betcha. Just use the table. And the strongest base? Remember what we just reminded you about regarding hydrogen carbonate ion? Is hydrogen carbonate ion not the strongest base in this PSI? Sure is. If you got any Santa Flush or Vanish at home, an Arm & Hammer, anybody got any Arm & Hammer at home? You know, orange box, white circle, strong muscle holding a hammer. Baking soda, sodium hydrogen carbonate. Acid, this time bicarb or hydrogen carbonate ion behaving as a base, not as an acid as it did in system F. So this is the H plus catcher. Well, if I add H plus to this, I'm going to make this stuff. And when I deprotonate this stuff, I make this stuff. What's the extent of this reaction? Large or small? Large. Now then, look again at the acid-base table. Immediately underneath, you'll see a note. You'll see some information about this stuff. What does the information tell you about this stuff? Because this is not carbonic acid. You might be tempted to call it such, but the truth of the matter is that hydrogen carbonate ion on protonation in water solution converts mainly, over 99%, to hydrated CO2 molecules, which also is a stuff that behaves as a Bronsted acid, but not nearly as strongly as true carbonic acid. But true carbonic acid is very difficult to form because of its instability. Now, this stuff is also not stable. It's more stable than carbonic acid, but this stuff isn't very stable. And the note also tells you that what does this readily do? If I try to form this in abundance, what will I see happen? I'll see this happen. Because when this stuff comes together with this stuff, I get hydrated CO2. That's what this formula represents. That's why the quotes are on there, to have you realize this is not a formula for true carbonic acid. It's a formula for hydrated CO2, which again is not very stable. Now then, this stuff. What do you know about the solubility of this stuff in water? CO2.
Outside.
You ever shake and air immediately open thereafter a beer that's warm? How about a soda pop? Warm. What happens? Warm beer, shake it up, open the top. What's going to happen? Same for a warm soda pop. Any carbonated beverage, if it's in an acidic system. And all carbonated beverages sold for consumption are reasonably acidic systems. Well then, is this or is this not very soluble in water?
It's not soluble.
I'm asking, you think this might have something to do with structure?
Yes.
What do you know about the structure of CO2? What's its shape? What's the shape of CO2 molecule? Linear. Now the bonds are polar, the carbon-oxygen bonds. But is the molecule polar? No. Because the carbon-oxygen bond vectors sum to 0 at the center of the molecule, which is the carbon atom. So this is a non-polar stuff. Water is highly polar. Water and CO2 are electrically quite dissimilar. So do you expect CO2 to be particularly soluble in water?
No.
Does that not account for what you observe if you shake a warm can of beer and then open up? Let's try this investigation. Here from the laboratory, I took some sodium hydrogen carbonate solution. This is half molar rather than 1/10 molar. This is from the 46 laboratory. Put a good slug of that in there. And now, I also took some sodium hydrogen sulfate solution, half molar, more concentrated than tenth molar. Let's bash the sodium hydrogen carbonate solution with the sodium hydrogen sulfate solution. Oh boy, Alka-Seltzer. Just like this chemistry told us, right? Now you know why this chemistry occurred. Because what we did was to demonstrate this reaction. No more, no less. H. I purposely have not written, at least yet, the PSI for the sodium sulfide solution, because I want to see if you have remembered how to write the correct PSI for this solution. What is it? Sodium sulfide by itself. Is that an ionic compound? An ionic compound, sodium sulfide. Yes or no? Yes. And these ionic compounds, on being dissolved in water, do what? Dissociate. So when sodium sulfide is dissolved in water, at the minimum it dissociates into sodium ions and sulfide ions. Now we have to pay attention to the PSI. In order to write the PSI, as always, we have to pay attention to the complete chemistry which occurs when the solution is prepared. Now we already have more or less taken it for granted that we don't have to pay attention to sodium ion from an acid-base standpoint. If sodium ion formed a hydrate that had any acidic properties of consequence, we'd talk to you about it. We'd have it in the acid-base table. But sodium ion doesn't form a well-defined hydrate. Hydrated sodium ion has no impact on pH in water solution. So it behaves neither as a Bronsted acid or base. But how about sulfide ion? Are you looking at the table? What do you know about sulfide ion? How strong is it? Stronger than hydroxide ion, isn't it? That means when sulfide ion is placed in water, and there's no acid in the system stronger than water, the sulfide ion will react with water to produce what? Sulfide ion plus water. Products are? I'm listening. HS minus, the conjugate acid of sulfide ion and hydroxide ion. So there's our PSI. And of course water. And if you write anything but this, it's not correct. If you write sulfide ion AQ, you've written something which is mythical.
What's the name for HS minus?
Hydrogen sulfide ion. You know, you pretty much name it from its formula.
Why would it hydrogen sulfide but not H2S?
Oh, wait a minute. Why would you expect it to go to H2S? Because in order to make H2S, you're going to have to protonate HS minus. Okay? Will HS minus react with water to a large extent? No. Will there be some H2S in this solution? You betcha. But its amount relative to the other things is negligible. All right? Now then, for this system, we're telling you two equations pertain. Well, PSI, strongest acid, is, what is it? Strongest acid. Use the table. Ammonium ion. Strongest base? Hydroxide ion. Products? Water, ammonia. Now, ammonia, like CO2, is also a gas under normal lab conditions. But if you run this reaction, you will not observe significant bubbling like we did when we made the CO2. Why not? Why is ammonia a lot more soluble in water than CO2? Why is ammonia quite soluble in water? Why can you make why can you make water solutions of ammonia which go up to 15 molar? Why is ammonia very soluble in water? It's highly polar, and what else? It's a hydrogen bonder. Hey, electrically these are very similar molecules. What's the extent of this reaction? Large. All right? Now we've also said two reactions of consequence. Do you think then you may be required to examine this system from a QPSI standpoint? Now we told you that in this system we have excess 1 molar ammonium chloride solution. Excess. Okay. So after this has taken place, practically speaking, which of these reactants has been eliminated? Hydroxide ion. So there's still an abundance of ammonium ions. Is there anything in here that ammonium ion might yet react with? HS minus. Because if you examine the acid-base table, you will recognize that after hydroxide ion is eliminated from this inventory, then the next strongest base is HS minus. So here comes H2S, which was asked about just a moment ago. But will H2S be produced in abundance by this reaction? Why not? This reaction goes to what extent? Small. That's it. So, with this chemistry, we ask the question, what about ammonium sulfide as a legitimate formula? Because you see, a lot of people, including many general chemistry textbook authors, they have the belief that I can make ionic compounds by bringing together any plus ion with any minus ion. That's really stupid. Because if I bring together a plus ion with a minus ion, and these two ions kill each other, because they react with each other vehemently, I'm not going to make a compound out of these two things. They kill each other. So I ask the question, if sulfide ion reacts with water, which we've already discussed, because that was part of our consideration to write the PSI for the sodium sulfide solution. If sulfide ion reacts with water, to an extent, practically speaking, of 100%, to what extent will sulfide ion react with ammonium ion? Is ammonium ion a stronger acid than water? Yes? Well then, if sulfide ion reacts with water, a weaker acid than ammonium ion. If sulfide ion reacts with water 100% extent, practically speaking, to what extent will sulfide ion react with ammonium ion? 100%! So can I make this compound? Hell no! So I warn you now, beware of bogus formulas like this. And how will we recognize a formula for a compound to be bogus? An ionic compound, which cannot possibly exist, regardless of my ability to write its formula on the board with a piece of chalk, or your ability to write its formula on a piece of paper with a pencil. or the dumb textbook author's ability to put it in nice type copy on a page in the book. You think that's going to make the compound exist? Not today. All you got to do is use the acid-base table. If there's any questions we ask you about acids and bases, will involve these acids and these bases. And see if the acid component, the cation component of the material, will react with the anion component, the base component of the material, to a large extent. If that's true, you cannot make that compound. Not as a stable entity. Now then, I also asked you, at the conclusion of yesterday's gathering, to consider this. Remember that? Now I'm going to ask the dirty question. How many of you did this? I told you from the very start, if you wish to have the opportunity to be successful, you damn well better do what I tell you to do. You have no choice. Because everything that you will be tested upon depends on what we do in this class. So if you don't do what I tell you to do in this class, your chances of being successful are hugely small. Or should I say, very no good. Now then, take note that I am considering mixing this compound with this compound. Am I talking about mixing solutions? If I recognize a system to be a solution, it's going to have this molarity label in front of it. These are compounds, pure compounds. Sodium oxide solid, because these are each ionic compounds, with ammonium hydrogen sulfate solid. I'm mixing solids, that's all. Do you expect any reaction to occur in mixing these solids? No. Statement. Since ions are the species of which ionic compounds are composed, it is legitimate on your part to inventory an ionic compound as its ions, because those are the species of which the thing is composed. They are the fundamental particles of which that material is composed. So an ionic compound, you can always, if it's a pure compound, you can of course write the formula just like we did here. Or, in order to assist you in getting at the acid-base part of this puzzle, or any other reactions which might occur, like we'll consider when we get to chapter 19, you can inventory an ionic compound as its ions. All right, let's do that. Na plus, O2 minus, ammonium ion, hydrogen sulfate ion. Okay? If I put together this combination of ions in a beaker or a test tube, whatever have you, shall I expect any reaction or reactions of consequence to occur? I'm asking. Look at the acid-base table. Look at the acid-base table and let it talk to you. What's the strongest base up here? Not only O2 minus a potent base, it's the strongest base listed on our table, isn't it? How about that? You see any acids on this? In this PSI? Is this an acid? Is this an acid? a base that reacts with water to an extent of 100%, and each of these acids, which are stronger acids than water. So I repeat my question. If I make this mix, do you think a reaction will occur? You're damn right. It's just like what I asked you about this ammonium sulfide stuff. If I put together this combination of ions, is this a stable combination of ions? Hell no. This base is going to react, and I mean react. With which of these acids preferentially? The stronger acid is hydrogen sulfide ion. Hydrogen sulfide ion. So let's write this. Now then, how many H pluses is this thing capable of extracting and behaving as a base? 2. Because if it takes 1, it converts to hydroxide ion, right? And hydroxide ion, you know, is a strong base in water. So certainly, per mole of this, I can well expect to extract 2 moles of H+. Okay? Now then, I have to pay attention to the quantitative aspect of this mix, because I'm considering a mole of this put together with a mole of this. So for this case, I can recognize that a mole of this kills a mole of this on contact. To make these products. Extent 100%. And I now will have a system which eliminates this, produces a mole of this and a mole of this, but for this reaction, where I've converted all of this to this, I now re-examine my PSI at this stage of the game and ask the next question, is there anything else which can happen in here chemically? What say you? What else can happen? What else will happen? This with this? You betcha. Now we've already looked at that reaction. This one is almost 100% extent. So, the upshot of all of this is to realize if I mix this with this, okay? What solid product will I wind up with and how much of it? What solid product will I wind up with and how much? That's my final question for this system. What solid product will I wind up with and how much? Well, after we run this reaction, let's heat it strongly. Let's heat it strongly, at least, I mean not strongly, but let's heat it to 101 centigrade, okay? We'll make this mix, okay? Make this mix. And heat to 101 centigrade in the open atmosphere. Okay? What am I going to wind up with? Because I'm at liberty to do anything I want in the lab. I can mix anything I want. I can heat it however I want. Will I wind up with any solid products? The main concern that I have regarding putting this question to you is to have you recognize you always have to pay attention to PSI.
Don't you end up with 2 moles of sodium?
Sodium element?
Yeah, the Na.
I don't think I'm going to make any sodium element which reacts explosively with water. I want to know what solid product I wind up with. You are not paying attention to the system inventory. Did we not start with 2 moles of this? Right? A mole of this has 2 moles of this, right? Did we do anything to remove the sodium ion from the system? Did we not also run a reaction in which this stuff was converted quantitatively to this stuff? And how much of this stuff do I have? 1 mole. So 1 mole of this with 2 moles of this makes me 1 mole of my solid product. Sodium sulfate. You can bet I'm asking stuff like this on Friday. You can bet on it. I guarantee. Now, what materials will leave the system as a consequence of heating it to 101 degrees? Water and ammonia. They go away. But that stuff won't go away. All right. And now we are ready to get at the real heart and soul of acid-base chemistry, which is the analysis of acid-base equilibrium systems. And when we plow through this, as I promised you earlier on, you will be capable of taking any water solution system and from an acid-base standpoint, determine the correct concentrations of each and every component of that water solution system whose existence depend on pH. And most everything in the system will depend on pH, existence-wise. That's pretty powerful too. To start, we first got to program you with more language. Ka, Kb. Look at the acid-base table. You see Ka values in that table? Right down the middle between the acid and the base, you see Ka values. By definition, Ka is a measure of the ability, the strength of a Bronsted acid to protonate what? Ka measures the ability of the Bronsted acid for the Ka values we have in our table. The ability of the Bronsted acid to protonate what? Water, the solvent, that's right. Because if I change solvent, I'm changing Ka values. Because water is a base, has a certain strength. If I measure Ka values using ammonia as a solvent, pure liquid ammonia, what's going to happen to my Ka values? They're going to stay the same, get larger, or get smaller? They're going to get... I'm going to measure Ka values for a bunch of acids using ammonia as a solvent. What kind of Ka magnitudes will I have relative to this Ka magnitude for the same acid in water? Is ammonia a better H plus grabber than water? You're damn right. So the Ka values will be considerably larger should I choose to measure them in ammonia. The hypothetical acid HX on reaction with water to make hydronium ion and X minus. By definition, the K for this reaction as an equilibrium is Ka for HX, the acid ionization constant for HX. There's the Ka chemical expression. We know how to write K expressions. Similarly, Kb, a measure of the ability, the strength of a Bronsted base to react with what? Water, the solvent, all the time. And in this case, produce hydroxide ion and the conjugate acid of the reacting base. So for X minus, the conjugate base of HX, the K value for this equilibrium is, by definition, Kb for X minus, which I've written over here. I've written it over here because I want to do some simple chemistry algebra on this expression. I want to multiply it by 1. I'm going to multiply it by 1 in this rather fanciful fashion. Hydronium ion molarity top and bottom. Do you agree that's multiplication by 1? Sure is. Now let's see what I have achieved with this multiplication. First, let me collect together these two terms. In water solution, what do I get if I multiply the hydronium ion molarity times the hydroxide ion molarity? I get Kw, don't I? So I will have Kw times the HX molarity divided by the X minus molarity, and also in the denominator, hydronium ion molarity. So focus on this remaining part of this expression and tell me if this part of this expression corresponds to anything you see on the board. Does this in any way bear a resemblance to KAHX? How does it compare to KAHX? It's inverted KAHX, isn't it? So this gives me KW over KAHX. And what's this equal to? It's equal to KB, X minus. The conjugate base for HX. So we've now recognized something. KW is always equal to, in water solution, the Ka value for a given acid multiplied by the Kb value for the conjugate base of that acid. So now do you see why in our acid base table it has not been necessary to give you Kb values? Because now you can calculate them, right? As long as you get the Ka value for the conjugate acid of any base in our table, you can calculate its Kb value. That's all there is to it. So with that, let's take a look at questions 12, 13, and 14. Now then, back to hydrogen carbonate ion. That's what question 12 is about. If we make a water solution of sodium hydrogen carbonate, or if you go to chemistry laboratory and steal some of this solution, it's a water solution of sodium hydrogen carbonate, 10th molar. If I observe the pH of this solution, will I find the pH to be 7.0, greater than 7.0, or less than 7.0? Because we recognize that a system whose pH is greater than 7.0 is a system said to be basic, and a system or a solution system whose pH is lower than 7.0 is said to be acidic. But if the pH is 7.0, we call it neutral. Okay? How will I find out? The answer to the question rests in determining Kb for hydrogen carbonate ion and comparing Kb for hydrogen carbonate ion to Ka for hydrogen carbonate ion. Now you see Ka for hydrogen carbonate ion on the table, don't you? These data are somewhat different than the last information sheet I had. I got some better data. I think I've now got Kb for hydrogen carbonate ion, Ka for hydrogen carbonate ion should be in there as 4.7 times 10 to the minus 11. Is that what we're seeing? Now I see this table in my sleep. I like that. It helps me rest. How do we get Kb for hydrogen carbonate ion? Have we now developed a relationship which will allow us to get Kb for hydrogen carbonate ion? Kb for hydrogen carbonate ion. So if imagine that here, I got Kb hydrogen carbonate ion. Then here, I want Ka for the conjugate acid of hydrogen carbonate ion. What is the conjugate acid of hydrogen carbonate ion? Is it in the table? What's its formula? It's hydrated CO2, isn't it? Because if I add H plus to hydrogen carbonate ion, we looked at this reaction not too long ago. We saw the bubbles and all that stuff. Okay? So, to get Kb, I want to take my take Kw and divide it by Ka for H2CO3. Quote unquote. Now then, the Ka for H2CO3, I've changed the values. When my memory's right, it's now written in this as 4.5 times 10 to the minus 7. Is that what we're seeing? How about that? So to do the arithmetic, I got to take 1.0 times 10 to the minus 14 divided by 4.5 times 10 to the minus 7. What kind of a value am I going to get, gee whiz? Well, let's take 4.5 and call it 4. What's 10 divided by 4? I'm listening. 2.5? Now I'm going to divide 10 by a number that's bigger than 4. I'm dividing it by 4.5, okay? So I've got to get a number that's smaller than 2.5. Maybe 2.2, something like that. Times 10 to the what exponent? 10 to the minus what? Because if I see you doing this arithmetic that I'm asking you to do now, with this thing, I'm getting out my sledgehammer and I'm going to smash that damn button thing and make you do it the right way. Nasty, ain't I? When I call this 10, then I'm talking about 10 times 10 to the minus 15. So here's the arithmetic I'm now asking you to do. 10 to the minus 15 divided by 10 to the minus 7. What is that? 10 to the minus 8. Come on now, that's not hard. So I got a Kb value for hydrogen carbonate ion, which is on the order of 2 times 10 to the minus 8. Now keep that in your mind's eye. 2 times 10 to the minus 8. Ka for hydrogen carbonate ion, we just talked about it. It's in the table. 4.7 times 10 to the minus 11, right? Which number is bigger? Ka or Kb? Kb, it's a lot bigger. About 500 times bigger. So tell me, is sodium hydrogen carbonate solution acidic, basic, or neutral? Acidic, basic, or neutral? Basic. Now then, let's see if you've got a feel for these numbers. Will sodium hydrogen carbonate solution be strongly basic or mildly basic? Well, I got to define some conditions then. Let's call strongly basic any solution which has got a hydroxide ion molarity of 10th molar or greater. 10th molar or greater. Okay? A sodium hydrogen carbonate solution. Strongly basic or mildly basic? Because this measure of its ability to behave as a base is a number times 10 to the minus 8. Is that suggesting that hydrogen carbonate ion is a strong base? No. Hell no! So what do you vote for? Strongly basic or mildly basic for sodium hydrogen carbonate solution? Mildly basic, you betcha. And we'll show you how to calculate the hydroxide ion molarity for that solution in the not too distant future. Now I got one more question to ask. If you are in the laboratory and you see this solution, which we got over there, in this solution, what is the principal Bronsted-Lowry acid-base equilibrium which exists? In that solution, sodium hydrogen carbonate was the principal Bronsted-Lowry acid-base equilibrium which exists. What's the first consideration you'll make to answer this question? What is it? Yes, you betcha. Okay, let's write it down. There's our PSI. So this principal Bronsted-Lowry acid-base equilibrium, do you think it's going to involve the strongest acid that's in the system in appreciable molarity? Reacting with the strongest base that's in the system in appreciable molarity? Yes and yes again. Well, from our PSI, tell me the strongest acid. What is it? Hydrogen carbonate ion, isn't it? What's the strongest base? What's the strongest base? What's the strongest base? What's the strongest base? Didn't we just talk about hydrogen carbonate solution being basic? Look at that PSI. Use that table. The strongest base is hydrogen carbonate ion. Remember, this is an acid. This is an interesting species. It's a stronger acid than water, stronger base than water. So the principal Bronsted-Lowry acid-base equilibrium in this hydrogen carbonate solution is in fact this. And that presents a problem if you want to calculate pH. Do you see the problem? pH is a measure of the hydronium ion molarity and indirectly a measure of the hydroxide ion molarity. That's what pH is. You see hydronium ion in this equilibrium? You see hydroxide ion in this equilibrium? Aha! So that leaves a problem, doesn't it? How do I do this calculation? Well, you will learn how. Statement: if you have some Arm & Hammer at home, and I bet many of you do, put a couple tablespoons full in water, small amount, put it in a pan on the stove. Heat the system. What do you think you're going to see happen in this heated solution of sodium hydrogen carbonate solution? Heated sodium hydrogen carbonate solution. What do you think you're going to see happen? You see bubbles? You're damn right. That's just what you're going to do. And in seeing these bubbles, are you going to be making the solution more acidic or more basic? You're heating sodium hydrogen carbonate solution. Does that have an effect on the pH of the solution after you heat it? What's the effect? It will make the solution more basic. Why? Is this not the acid component of this reaction? But this acid component does what? It falls apart and goes away. Ah, but this doesn't go away. And this is a much stronger base than hydrogen carbonate ion. All comes from PSI. Always pay attention to what's in the system, and then you can always answer questions like this. And if you forget PSI, goodbye, game is over. Now then, other questions here should be immediately obvious. Let's go to this. Ka water. I've seen many textbooks follow this up because they forget the definition of Ka. You see this reaction? You think this reaction corresponds to water behaving as an acid? Does this reaction correspond to water behaving as an acid? Absolutely. And it's giving H plus to the solvent, isn't it? And what's Ka by definition? Now let's talk about it by definition from a chemistry standpoint. Ka acid is the molarity of hydronium ion times the molarity of the conjugate base, all equilibrium values, divided by what? Is that? The molarity of the reacting acid? See that there? HX in the top there? Good. So here's Ka water. And this is the part of the puzzle that a lot of people who don't understand this chemistry leave out and follow this up. Now, I can take one of these waters as solvent. Pardon me. But the other one is the reacting acid water. And I got to put that molarity in there to keep with my definition of Ka. So, Up top, I got Kw, which is 1.0 times 10 to the minus 14. And we've already answered this. What's the molarity of water in straight water? 55 to 2 sig figs, isn't it? And so if you do this arithmetic, the 2 sig figs, you're going to get this number, which you see on our acid-base table, is the Ka value attributed to water. And if you look at this, you realize this also defines Kb water. So Ka water, Kb water are identical. So what's Ka hydronium ion? You see it on the table, it's 55, don't you? How do we get this Ka value for hydronium ion? Well, we could use this, can't we? 1.0 times 10 to the minus 14 equals Ka hydronium ion times Kb for the conjugate base of hydronium ion. What's the conjugate base of hydronium ion? Water. 1.8 times 10 to the minus 16. So if I take Kw divided by 1.8 times 10 to the minus 16, what do you think I get? 55. Or, if you want to do it this way, hydronium ion plus water, because that's the way Ka is defined for chemistry and water. Products, hydronium ion plus water. Now, solvent. But this stuff is product water. So Ka hydronium ion is hydronium ion molarity times water molarity divided by hydronium ion molarity, and there it goes. Water molarity 55. All done. All follows from the definition. Now, how do we get Ka and Kb values? Watch out for the wise guy student who says, look them up in the table. Because a long time ago there was no table. Somebody had to develop this table. And the way the table is developed is go to the laboratory and make measurements. So let's imagine we're back in the world of chemistry many years ago, and we don't know Ka for acetic acid. But we know its formula. Since we know its formula, we can know its formula mass. So I prepare carefully a water solution of acetic acid, say 0.300 molar acetic acid, and I observe the pH for this solution, and I get 2.63 to 2 sig figs. Remember, 2 sig figs? Not this. So I take the antilog of this to get the hydronium ion concentration, for which I get 2.3 times 10 to the minus 3. And I recognize by definition this is the equilibrium that corresponds to Ka acetic acid. So I write Ka acetic acid, and I take advantage of the results of my measurement. 2.3 times 10 to the minus 3 I put in here. And I look at the stoichiometry of this reaction, because if acetic acid reacted with water in this solution to develop a hydronium ion molarity of 2.3 times 10 to the minus 3, what's the acetate molarity that's been developed? 2.3 times 10 to the minus 3. And now, the final part of the puzzle is, what's the equilibrium molarity of acetic acid? Because in an equilibrium constant expression, you have equilibrium values, and that's all. What is the equilibrium molarity of acetic acid in this solution? Well, here's the label on the bottle. Is that the equilibrium molarity of acetic acid? What is the equilibrium molarity of acetic acid? To answer this question, we have to introduce you to another piece of important language. It's called material balance. Because in any acetic acid solution, we either have acetic acid molecules, or what we get when these things do their acid thing and become acetate ion. So what this this material balance is equal to for this acetic acid solution, okay, is this. For acetic acid, or stuff derived from. acetic acid. And the stuff derived from acetic acid is acetate ion. And the acetate ion molarity is 2.3 times 10 to minus 3. So here is my determination of the equilibrium molarity of acetic acid. This is what I started with, and this is how much of it got reacted, converted to acetate ion. So this becomes 0.298. And when I do the arithmetic, I will get 1.8 times 10 to minus 5. Now this leads to a very important generalization. Here's the generalization. If I prepare a solution of a weak acid, water's my solvent, or a weak base, and that weak acid is the only stuff in the system which affects pH beside water, or in the water solution of the weak base, the only stuff in the system which affects pH beside water is the weak base solute. I can take advantage of recognizing that by the stoichiometry of this reaction, Ka for the acid solution is x squared over m sub I minus x. X squared over m sub I minus x. Do we see where this comes from? X is the hydronium ion molarity for the acetic acid solution. X is the acetate ion molarity. M sub I is the label on the bottle. And X represents the acetic acid that converted to its conjugate base, acetate ion. That's all there is to it. So, let's take a look at this recipe and use it to calc this molarity for this solution. Well, we got 1.8 times 10 to minus 5, and we got x squared over 0.10 minus x. Where x will in this case represent the hydronium ion molarity as well as the acetate ion molarity for the 10th molar of 2 sig figs acetic acid solution. Now before we do this arithmetic, I want to go back to this solution, which is 0.300 molar acetic acid. Do you realize if I take some of this solution and dilute it threefold, I'll have this solution? You did stuff like this in lab. 45L, you did this. And now you're making more solutions by dilution in 46L. 3/10 molar acetic acid diluted by a factor of 3 gives me 10th molar acetic acid. And for my 3/10 molar acetic acid solution, I know the hydronium ion molarity, don't I? Here it is. Question. Can I get a good value for the hydronium ion molarity for 10th molar acetic acid by taking this molarity, the molarity of hydronium ion in 3/10 molar acetic acid, and dividing this by 3? Will that give me a good handle on the hydronium ion molarity for that solution? Yes or no? No, why not? Will the hydronium ion molarity for this solution be larger or smaller than this number divided by 3? Larger. A good deal larger. Because what happens to ionization extent when I dilute? We've talked about that, haven't we? If I have this acetic acid water equilibrium existing in my 3/10 molar acetic acid, at the instant at which I dilute it to prepare my 10th molar acetic acid, this equilibrium is killed. And what reaction takes place to get me back to equilibrium? This one, doesn't it? So I'm going to make more hydronium ion. I will not increase the molarity of hydronium ion. You can't get something for nothing. But I'll make more hydronium ion if I take this solution, all of it, and dilute it threefold to make that. Now comes the arithmetic. Is this a quadratic? course it's a quadratic. Am I going to solve this with a quadratic formula? Hell no. Never. It interferes with my understanding chemistry. But now I'm going to take advantage of realizing something. If m sub I minus x equals or about equals m sub I, then x is equal to Ka times m sub I to the 1/2. Woohoo! Where'd all that stuff come from? If this is equal to this, because 0.10 minus x is the same as 0.10, then I cross multiply. Here's m sub I, here's Ka, x squared, so I take the square root of that and I get the hydronium ion molarity. Well, let's play that for this solution. 0.10 times this gives me 1.8 times 10 to the minus 6. All right? So if I want the hydronium ion molarity by this arithmetic, I do this. Square root of 10 to the minus 6. What is it? What is it? Square root of 10 to the minus 6. 10 to the minus 3. If I see any push buttons with that, smash! Square root of 1.8. Did you learn the squares of numbers from 1 to 25 in high school? Then learn it now, damn it! What's 1 squared? Woo! 1. What's 2 squared? 4! Square root of 1.8. If I take 1 and square it, I get 1. If I take 2 and square it, I get 4. Which number squared is closer to 1.8? 1 squared or 2 squared? 1. So without any monkey business, I know that the square root of 1.8 is a number that's closer to 1 than it is to 2. We can start with that. And now I'll play this game. What's 13 squared? 169. What's 14 squared? What is it? 196. 13 squared. Let's move to decimal point. 1.3. That gives me 1.7, doesn't it? 14 squared, 196. Let's take that to 2 sig figs and move to decimal. I get 2.0. Which of these is closer to 1.8? 1.3 squared, isn't it? So guess what? I've just found out that by this arithmetic, for this solution, the hydronium ion molarity is 1.3 times 10 to the minus 3. Now, one last $64 question. Is this correct? Well, let's try this. Here's m sub I. And here is the hydronium ion concentration, which I've calculated. Right? If I take this value from this value, do I make this value get smaller? Do I change this value? Yes or no? No! You're damn right. So this is exactly on the nose. And I didn't have to fool around with any quadratic, did I? You pick it up from this point tomorrow in discussion, and tomorrow lecture we're going to get on with indicators and stuff like that.